Welcome everyone. My name is Dominik Durner and in this video I am presenting Crystal, a unified cache storage system for analytical databases. This is joint work together with Patricia Andremoli and Dina Lee from Microsoft Research. In recent years, more and more applications move to the cloud, and database engines are no exception to this rule. Especially the resource elasticity is one of the main drivers, because now the compute nodes scale independently of your storage. This allows for higher flexibility, because when your system hits load, you can simply spin up more compute nodes. However, this disaggregated storage architecture has some additional challenges. First of all, we have a higher latency for accessing data because we have to go to the remote host. Secondly, we're limited by the bandwidth of the network connection, which is usually lower than the bandwidth we're used to from a local SSD. That's why we have seen a renewed interest in caching data at the local compute node. Current caching solutions usually operate at the file or at the block level, and examples include the Databricks Delta Cache, Alaxio, or the Snowflake caching layer. These block-level caches have the downside that they can have very poor cache utilizations, especially when the number of useful records in one block is very low. This results that the cache has to cache the full block and therefore wastes precious cache space. Additionally, cloud providers now allow to push down predicates to the remote storage and return the predicate table. However, it is unclear how to add these predicated table information into these caches. So let's have a short look on an example. Here we have 3 queries and 4 blocks. Each of the queries accesses parts of each individual block. When we now have a traditional block level cache with a replacement policy such as LAU, we can see that none of the queries could be computed completely locally. However, if we now aggregate all of these information which is really needed for the queries, we can see that this information would fit in the very same space. So, with semantic caching, where we actually store the relevant information, we can see that all queries can be computed fully locally. That's why semantic caching can solve these challenges. However, semantic caching has some open issues. First of all, how can we make it practical for such modern analytical workloads? Secondly, how can we actually integrate semantic caching across multiple database management systems with minimal disruption? And lastly, how can we balance short-term adaptiveness with long-term optimality of the cache data? That's the reason why we developed Crystal. Crystal is a storage middleware between the database management systems and the storage layer. It can be seen as a cache management system which is co-located at the compute node of the host database management system. With our easy-to-implement connectors, the host database management systems, for example Spark, can almost stay unmodified. Crystal itself uses semantic regions for all data interactions and the caching. These semantic regions are carefully designed for minimal overhead in such modern analytic workloads. The database management system pushes down the predicate to Crystal, and Crystal decides whether this predicate can be answered locally or downloads the relevant parts from cloud storage. We also trace all of the predicates from the database management system to only store the data of interest. We do so by splitting the cache. We split it into a short-term and a long-term cache. The long-term cache uses an oracle which computes the optimal set of long-term cache data, whereas the short-term cache is used to respond to workload changes quickly. So let's have a look how Crystal transforms predicates to semantic regions. So first we receive the predicate tree from the database management system. On the leaf levels, we can see the column predicates, which are combined with AND and ORs. However, arbitrarily combined AND and ORs are hard to argue about. That's why we transform it into DNF. With DNF, all the ANDs are at the lower level of the tree and the ORs are on top of it. This allows us to see the individual AND predicates as hyperrectangles, and the OR is the simple combination or union of these hyperrectangles. Note that the hyperrectangles may overlap. Crystal embraces this overlapping in contrast to previous work in semantic caching. We do not split into non-overlapping regions anymore because this is very expensive. Especially when you have high-dimensional data and many cached elements, this will partition the data space in many parts. However, each individual part requires more work to be done at the host database management system. We did a preliminary experiment where we saw the more regions we return, the higher the latency is. That's why we try to minimize the number of regions returned to the host database management system. I already mentioned that the Oracle tries to find the optimal set of data items stored in the cache. This problem can also be seen as a knapsack problem. Given a number of regions, we want to find the best optimal set of regions fitting in our cache budget. There are two ways to solve this issue, either perfectly with, for example, dynamic programming, which is rather expensive, or you approximate the solution with a greedy approximation, which in reality works often quite well. The regular 0.5 greedy zero approximation works as following. First, we sort all items according to the cost-benefit ratio. Then, we pick items according to this cost-benefit ratio until a budget is reached. Both algorithms, the greedy approximation and the DP version, cannot handle overlap. That's why we need to adapt the algorithm here, and we do so by re-evaluating the cost-benefit ratio after picking an item, because now we have a different number of cached elements, so the overlap may change. So let's have a look at which geometric overlap possibilities we have. So in this example, we can see that our new candidate set is actually a full superset of something within our cache. Then we reduce the weight and the benefit by the values of the picked items there, so the white items here. That's allowing us to actually add the new candidate to the cache by simply removing the old ones and therefore adding only the delta. What happens if my candidate is a full subset of something within the cache? Then we can reduce the benefit to 0 because this doesn't allow us for any additional value. And lastly, it can happen that we have a partial overlap with some elements within the cache, so an intersection. There, we reduce the benefit by the history elements that are covered completely by both regions. Our Oracle uses the history elements for both generating the regions to cache, but also to calculate the benefit. That's why it's possible that we might overfit. Therefore, we develop the approximative merging of regions. There, we merge neighboring regions either as an intersection or within an epsilon distance. Then, we compute the cost-benefit and rank these new regions. And lastly, we add the best candidates again back to the knapsack algorithm, which then computes the new cached items. So how does this approximative merging work? So in this example, we see on a 2D space multiple predicates from our host database management system. Now, we apply approximative merging and find these light blue rectangles. Additionally, we see new queries coming from the database management system, so in the next iteration, we can find the region of interest more easily, which we then feed back to the knapsack algorithm. With that, we can actually find the generalized region of interest over time with our approximative merging strategy. So let's have a look at some of our numbers. Here, we compare against Alaxio in a Spark setting. So we add Alaxio or Crystal to Spark and run queries there. We look at how much cache is needed until we see query improvements, which is shown here by query latency. We can see that Crystal learns the regions of interest quite quickly, even with very small available cache size of only 10% according to the remote data. When we look at Alaxio, we can see that way more cache is needed to actually achieve the very same results. The reason being is that the file and block level caches fail to utilize the caches well. We also did an experiment with different caches within our Crystal setting. We used a regions workload, which basically defines 5 regions, which each span roughly 10% of the tuples. And each region again has queries which take 10% of the tuples within a region, so in total 1% of the tuples. So when we look at the regions workload, we define different competitors. We have the vanilla Spark competitor, we look at a short-term LRU cache, our long-term dynamic programming knapsack algorithm, and our proposed Crystal algorithm. Again, we plot the query latency, and the red dots show the average. We can see that the average for having no cache is around 18 seconds, whereas with Crystal, we can cut this query latency time by almost a factor of 4. So overall, we can say that Crystal computes the optimal set of regions while being responsive. It's agnostic to the database management system because it's connected with very lightweight and easy to implement connectors. In the paper, we show also results with another database system, namely Greenplum. Our semantic regions allow for better cache utilization and significantly improve the query latencies. Thank you.